Hi friends, my name is Tris, and this is No Boilerplate, focusing on fast, technical videos. Rust is the senior developer's dream language. Certainly it is mine. For the first time in my 15-year career, I feel that I have found a language that lets me confidently write not just high-level application code, but low-level driver code and everything in between too. What gives me this confidence is Rust's borrow checker, algebraic data types, powerful macros, and the unsafe system, all kept sane by the friendliest compiler in the business. I've explained the joy of Rust at length on this channel. I shan't repeat myself here. See my playlists if you're curious. However, some of what I have mentioned breaks down when interacting with async Rust. Async code seems alien. Some people even say it's not Rust, it's a different language hidden inside it, but the problem is simpler than that. My core issue with async in Rust isn't that it's bad or broken or unusable. It's actually nothing short of miraculous. The problem is that it threatens what I consider Rust's golden contract with its users. If you use references, the compiler will make your life easy. You get Rust's superpowers for free if you use Rust's ownership model with its two kinds of references, shared and exclusive. In my How to Learn Rust video, I recommended that students first don't use references, use ownership and share nothing, then copy and clone everything, and then only use references when the compiler tells you to. I promised that following this would eventually teach you how to use most of Rust properly. But for async Rust, there is a part 4, which rather complicates matters. Though the compiler is getting more and more helpful with each iteration, async is still a sharp edge, especially for newcomers, because it kind of forces you to learn everything. I dedicate my video scripts to the public domain. Everything you see here, script links and images, are part of a markdown document available freely on GitHub and at my website, namtao.com. I'm delighted to say that this video is sponsored by friend of the channel, Let's Get Rusty. In addition to being a fellow Rust YouTuber, Bogdan runs Rust training both corporate and personal with a new cohort starting each month. Visit letsgetrusty.com/startwithtris, link in the pinned comment, to find out more about the training. And thanks so much to Let's Get Rusty for sponsoring this video. I'm going to discuss concurrency and parallelism today, and despite the assumptions of the Tokyo Crate, these are very different techniques, and we should tighten up our definitions before we continue. You and I, as humans, are single-tasking creatures. We can do one piece of mental work at a time. Concurrency is how we actually multitask, either by picking up one task at a time and working on it until we switch to another, or by rapidly switching between tasks, completing them all a bit slower. This illusion causes people to think we are working on things in parallel when in fact it's near impossible for us to do more than one task at a time. A single CPU with a single thread multitasks with concurrency too, but because the CPU can switch tasks so incredibly fast, it really can feel like multiple things are progressing all at once, especially when many of the tasks are I/O bound, waiting for external inputs such as network or disk. A single human only has access to concurrency. Modern computers, of course, can also access parallelism. Parallelism is simple to explain, if rather complicated to get right. For example, in a group of 3 people, we each take a task and work on them in parallel until they are done. And it's the same with parallel processing in computers. The problem arises, just as in group work, when one person seems to never quite finish a task. A thread may never finish. When we spawn it and give it some work to do, we can't guarantee it will ever return the results of its computation. Not a problem for laissez-faire fuck-it-ship-it languages, but a real problem for Rust. The compiler doesn't just want to know what our data is, with its rich types, but when our data is, by augmenting those types with lifetime annotations. This is a critical pain point that we will come back to later. Okay, finally, some code. Let's say we have an expensive function. Perhaps it makes a network request, like here, that we want to run in the background while we do other things. To do that, you might reasonably reach for async, like in other languages. Let's see what async looks like in Rust. And now that async standard is deprecated, what that usually looks like is the Tokyo Crate. So here we have rewritten our expensive function into one that makes the GET request asynchronously. We spawn it with the Tokyo executor and await the returned future. Easy, but this doesn't compile. Looking at the implementation, it seems that the spawn blocking function requires references to have the static lifetime, an annotation that asks the compiler to prove they will be valid for the entire execution of the program. This is not the case for our URL shared reference. The current lifetime is tied to the calling function's body, which, in our example, immediately terminates. Okay, fair enough. The full cargo error is very clear on how to solve this. We simply obey the compiler and dutifully add the static lifetime to the reference. This syntax requires the compiler to prove that the URL shared reference is valid for the entire execution of our program, not just for the duration of this single function. The compiler is now happy, and if the compiler is happy, I'm not happy, folks. Usually when the compiler is happy, I am happy, but today I am not. Not at all. In fact, I'm kind of furious. Of course you can get fearless concurrency if you only send around static read-only data. That's actually super unimpressive. Forcing all our references to be valid for the lifetime of the program effectively turns off a large part of the borrow checker. I thought this was Rust. No compromises. I want to have my cake and eat it too. Don't worry, this story has a happy ending. The crux of the problem is that parallel async tasks, which Tokyo assumes we'll be using by default, can run for an unknowable amount of time as far as the Rust compiler knows. I told you we'd come back to this problem. This means that all references must be valid forever, static. This is fine for something like a server handling requests, but do I really need to throw out borrowing just because I want to make a GET request? No, and the good news is that this isn't some intrinsic property of Rust. For instance, it's not like this using native OS threads. There we are. Oh no, the Hydra just won't stay dead. Stay strong, Hercules, I have just the weapon. Marvelous. Scopes are genius. All threads are joined at the end of a scope which blocks until they are done. This guarantees to the Rust compiler that all threads inside the scope will finish before it returns, which restores my favorite feature of Rust, borrowing. The URL shared reference can be passed into a thread and then, at some point in the future, can be released at the end of the scope. My generalized advice to get fearless parallelism is to tightly scope it. Here's how it works. The function borrows a shared reference to the URL variable, then spawns a thread for processing it. At the end of the scope, all threads are joined, and finally, the shared reference is released. It doesn't look like this using async with Tokyo. We start off similarly, borrowing URL. However, Tokyo requires all references to be static, so the static lifetime propagates up the call stack to wherever URL was first borrowed, even if that was in synchronous code. Then we spawn a task on the executor using spawn blocking, and the work begins as we await the result of our future. While both threads and Tokyo tasks are quite similar, the former feels like coding in Rust, whereas the latter feels like something else entirely. Some people, when confronted with a programming problem, think, I know, I'll use async, which of course means they now have two problems, or perhaps 200 if they use Tokyo. One of my favorite things about Rust is that you can look at a function's code and reason about it without building an error-prone runtime in your head to simulate it on. So much information is encoded into the type system, including the granular purity model of ownership that you and the compiler can reason about your code in ways that other languages can only dream about. See my purity video for details there. Async processing requires a runtime, and if that runtime is the most common one, Tokyo, this causes static references to infect huge parts of your code. The issue with this static everywhere pattern is that it forces you to make guesses about your program's global runtime state, when before you could just reason about one function at a time, confident that the compiler is keeping the rest of your program in line. This building up of your program state in your own mind is not what we're here for. Your brain won't scale, but the Rust community has your back. Part 3. Solutions. Here are some examples of writing async code in Rust in ascending order of how much I like them. Number 4, Arc. I'm not interested in runtime borrow checking with Arc. I'm interested in Rust zero-cost native compile time borrow checking. However, some problems simply require using Arc and Friends. Check out the linked Code to the Moon video on alien data types for more details there. Number 3, Tokyo Scope. This allows behavior similar to the thread scope example. Because all futures are guaranteed to have finished by the time the scope ends, references can be dropped after use. However, this is not without drawbacks compared to a pure threaded example. A runtime is not free. By definition, the more logic you push to runtime, the less the compiler can prove at compile time. Let's keep going. Number 2, small. The small crate is brilliant because it doesn't commit to the original sin of conflating concurrency with parallelism. Both are available in small, and you opt into what you want. As the name suggests, it's also tiny. The entire executor is around 1,000 lines of code. You can even use Tokyo-based libraries with small by using the async compat crate, which adapts Tokyo futures and I/O types. Number 1, Rayon. If you just want to speed up an inner loop in an otherwise synchronous program, don't infect it with async everywhere. Just use Rayon. It magically converts any iterator into a parallel iterator, reminding me very much of Haskell's par keyword. Its data race-free work-stealing parallelism has made it a rock star in the Rust world for a decade. Read this article if you'd like to know how it works. But don't forget about the runtime that the operating system already gives us for free. Modern Linux can manage tens of thousands of threads, which means you might not need to infect your code with async, even for a high-performance service. Using native threads might also make your debugging easier. Instead of Tokyo-specific instrumentation, such as the excellent tracing crate, you can use any tools from the Unix standard thread management ecosystem. In Rust, you don't have to use async, and even if you do, you have more options than Tokio. The core of my advice is that if you scope the async part of your code tighter than the whole program, your life will be better. You can keep writing Rust with the compiler as your trusted guide, because async isn't real and can't hurt you. The rumors are true. After producing fiction podcasts for 5 years, I'm finally releasing my first Talking Head style podcast. On it, my friend Robin and I decapsulate many of the topics I talk about here on my channel. I've posted episode 1 right here in the No Boilerplate feed. Click this video or the link in the description, and episode 2 is out early for patrons now too. Listen at decapsulate.com or wherever you get your podcasts. If you don't have a podcatcher yet, I use the Pocket Casts app and love it. They're not even sponsoring me yet. Thank you so much for watching and listening. Talk to you on Discord.